You know you're going to go visit Grandma and you know that you don't want to put all your eggs in one basket. Or a little more formally, it's been shown that most people prefer to avoid losses more than they prefer to get a gain, and that by having different securities, that tends to be preferred. Let's start with some pretty basic fundamentals. The amount you have in each security in a portfolio, when divided by the total amount of the portfolio, is a weighting, and that the sum of the weights add to 100%. And it turns out if you take those weights times the return that you get from every security and add them up, you get the return to the portfolio, say as a percentage, or it could be a decimal. And the returns are, it's actually the net yield, is the price of the security at the end of the period minus the price of the security at the beginning of the period, plus any dividends divided by the price at the beginning. And of course, you may say, well, gee, why don't I just add up all the dollar amounts times the returns, then divided by the dollar amounts? And I'm not going to bother with a proof. It's almost trivial. It's actually the same thing. Now, the risk of the portfolio measured in variance is a matrix, a column and row total. That's what the double summation means. And the weight for each one of them, for each row and column, times the covariance of each security, I to J. Now here a little bit of mathematical housekeeping is probably going to be helpful. Here's our matrix. It's a square. And along the diagonal, that's where I equals J. That's where the cross products, the multiplication of each one of those differences from the mean, are multiplied each other. And if it's the same, then it's squared, but that's the definition of a variance. Here, many times, the development continues, and Gruber is a great source, or add Brown and Gutzman for later editions, and that is you have a naive portfolio. That means anybody can do it, which means you put equal weights for each security. You know, if you have 4 of them, you put 1/4 in each security. And as we saw, if we separate where I equals J from those that are not equal, we have invariance terms, and thus we have for the remaining non-equal covariance terms the n squared minus that n. And let n become big, large, huge, approaching infinity. And, well, one of the n's cancel. And look at that. When n becomes big, the variance term, the idiosyncratic risk of each individual company, approaches 0. And that goes toward the idea that you're really only holding a market portfolio, and frankly, you can almost avoid the individual company news. And that's all well and good. Maybe you do want to put, say, for 4, 1/4 in each, but maybe the companies are not the same size. You may have GM and Ford, and on the other hand, Fiat, Chrysler, and Tesla. And maybe you might want to weight them in a different way. And offered your consideration, a la Sharp, if you will, is maybe put those that have a larger risk, have a smaller proportion, and vice versa. And that's to take the reciprocal of the standard deviations and weight them. And when you substitute that into the equation, it becomes at first unwieldy. Good grief, look at that thing. But remember, the definition of the correlation is the covariance divided by the standard deviations. And when you solve for the covariance, plug that back in, the standard deviations cancel, and all you have left for the portfolio variance is the correlation times the square of those weightings, which you recall is the summation of the reciprocals. We'll do an example. Here, let's say we have 4 securities. Each has a standard deviation of 0.1, 0.2, 0.3, 0.4. And I'll note, by the way, that the annual standard deviations are a function of the square root of time. So with roughly 256 trading days a year, work with me here, the square root of that's 16, so it'd be 16 times the daily standard deviations. And, well, let's see, the reciprocals of those respectively would be 10, 5, 3 1/3, and 2 1/2, and they total 20.833, and thus the weights would be 0.48, 0.24, 0.16, and 0.12, and of course, it adds to 1. So if you plug in this example in our 4x4, that's 16 cases in our matrix, and we have that weighting that we noted was the square of the reciprocal sums, and well, remember that's the variance, so we take the square root of that, and if every one of the correlations happened to be perfect as an extreme case for computational purposes, we would get back the standard deviation of this portfolio as being 0.192. And you think, say what? Hold on, we'll prove that's right. Here, in the special case, if each and every single correlation was 1 perfect, I know, work with me here, and if that were the case, we would just take a linear weighted average of each standard deviation, and again we get 0.192. And I showed my work for full credit. And going back to the bottom resultant equation, we see that we're squaring a term which increases as we add securities, and we do note that each standard deviation has to be at least less than 1, otherwise you'd get a negative price. So that means the reciprocal's larger, the inverse of it is smaller, squaring it of it makes it even smaller, but this is just merely an exercise. What you really want to do is something else. Here's a 5-asset portfolio. I chose this extreme case to illustrate the point. We have 5 securities. E notably is the worst in both regards. Lower right-hand corner has the lowest return, that goes up and down, has the highest risk, going to the right. And yet in spite of that, it's included in an optimal portfolio where you want to go up and to the left, highest return, lowest risk. Not a lot is included, but some is included. I like to point out it's something like adding pepper to soup. You don't want a lot, but you may want a little bit with Dr. C Invests.